Thank you so much. Okay. Hi, everyone. So as Sophia said, I'm Nikki. I'm a postdoctoral Rubin Fellow here. Postdoctoral meaning that I went to college and really liked school and I was like more. And so then I went to a grad school and really liked it some more. So I wanted more. And now I am postdoctoral. So I got my PhD and I'm still learning and it's great. Highly recommend is what I always say. I'm affiliated with the Rubin Observatory, which, raise of hands, has anyone heard of the Rubin Observatory? Yeah, okay, so a little bit. So it is an observatory that hosts a telescope, the Simonu telescope in Chile, and it actually just went online this year and started collecting data. So you are hearing this talk at literally the perfect time. Yeah, so I wanted to give a talk about the observatory that is letting me be here today, and specifically a little bit about like the namesake. Yeah, so we're going to learn a little bit about time domain astronomy, which is what this observatory is known for, but we're going to start with a little history of Vera Rubin. Yeah, so here's our order of operations. So we're going to start with Vera Rubin, talk about the telescope, move on to time domain astronomy, and then I'll give you just a brief glimpse into like what I do. And hopefully you all have lots and lots of questions and come mob me afterwards. Okay, so who was Vera Rubin? So this is her. We can't really talk about the observatory without talking about Vera Rubin. So she is was an American astronomer. She unfortunately passed about 10 years ago, which is why we're able to name an observatory after her. Yeah, so she was born in Philadelphia in 1928. She moved to DC with her family, and at 10 years old, started watching stars from her backyard and developed a great interest in astronomy, which is how many of these stories go. And we are super lucky that she did, because she has an incredible legacy of changing astronomy forever. So, to name a few accomplishments, she received the Bruce Medal, the Gold Medal of the Royal Astronomical Society. I literally had to write these down because there's too many. The National Medal of Science. The New York Times once described her legacy as ushering in a Copernican scale change in cosmological theory. As a reminder, who here has heard of Copernicus? Yeah, okay, so super famous for changing our understanding of the Earth being the center of the universe to, or at least the solar system, to the sun being the center of the solar system. So in cosmology, Vera Rubin did that. So huge name. She's just a little important, is what I'm trying to get at. So let's talk about what her legacy was. Okay, here we have an image from the James Webb Space Telescope, so not Rubin, unfortunately. This patch of sky is actually the equivalent of you holding a grain of sand out at arm's length up at the sky. And that's like, that would encompass all of what we're seeing here. This is called a galaxy cluster. It hosts like thousands of galaxies and therefore billions of stars. So let's break down what that means. So here we have a galaxy. A galaxy is a collection of a bunch of things: stars, dust, gas, and specifically, a galaxy is holding these things together via gravity. Let's talk about gravity. Okay, we all understand gravity to be the thing that is keeping us from flying off of Earth right now, right? If we like toss a ball into the air, it's gonna come back, kind of a thing. The most important thing for Vera Rubin's story is to understand that gravity is related to the distance from some massive object. So here we have our little astronaut, Vera Rubin. She's standing on Earth. They both have mass, Earth's mass being greater, and she's experiencing some force of gravity. Now, this force of gravity would be different if she were floating out a ways away from the surface of Earth. Specifically, she would feel a bigger force of gravity standing on Earth than moving away. So biggest thing to remember, you're going to feel gravity, and specifically the force of gravity, stronger the closer you are to your massive object. Yes? Okay. So let's look back at this picture. So we have gravity. We have our galaxy, which is using gravity to hold together stars, gas, dust. And here we have our galaxy cluster, which is sort of another step back, where we are now using gravity to hold together thousands of galaxies. These are some of the largest objects in the universe that are held together by the force of gravity. So the scale of these things is huge. So let's go back to the 1920s. In the 1920s, if you asked an astronomer, or really any human on Earth, what the universe was made of, when looking at this picture, they would have told you this. Our pie chart is all stars, galaxies, planets, gas, dust, basically whatever we're seeing in that image. Anyone notice, I guess, raise of hands, anyone think anything's like missing from this? I mean, it has been 100 years. Yeah, I'm seeing a few hands. Yeah. So in the 1930s, we meet astronomer Fritz Zwicky, who noticed something strange about our good friend, the galaxy cluster image that we were looking at before. So he's looking out, and he saw that the clusters are moving way faster than they're supposed to be, per our understanding of gravity. He thought that maybe there's something extra that he can't see that seems to be sort of adding this gravitational pull. And he decided to call this dark matter because it had some sort of a mass that was affecting things, but he couldn't see it. And so here's his big, like, famous quote. He said, "If this should be verified, it would lead to the surprising result that dark matter exists in much greater density than luminous matter," meaning the matter we're seeing. This is Nikki's paraphrase of it, which is, wow, these are moving so differently from what I'm used to seeing, because of gravity. There must be more there, and whatever it is, there's a lot of it. Okay, so someone needs to check this work. And here we meet Vera Rubin. Okay, so Vera Rubin graduated with her undergraduate degree in astronomy in 1948. She wanted to pursue a graduate degree in astronomy, and she applied to Princeton University because she was brilliant. And anyone want to guess what happened? In the 1940s at Princeton University, Rubin was denied because they didn't accept women back then. I actually have a fun little quiz for you all that hopefully won't make you too sad. Makes me a little sad. Does anyone want to guess what year Princeton revoked their policy of denying based off of gender discrimination? So we know it wasn't 1948. I'm hearing 1967. I'm hearing 1970s, maybe. It's 1975. I looked up University of Toronto's numbers. Does anyone want to guess? Because it wasn't always. It was also all male, but they were a little ahead of the curve. Does anyone want to guess when U of T enabled the admissions of women on our campus? Ooh, I'm hearing 50s. Okay, 60s. I'm gonna go, it's actually earlier than that. I know. Okay. I know. We're really patting ourselves on the back here in Canada. I grew up in Wisconsin, so I'm actually very happy to be here for a multitude of reasons. But yeah, this one too. It was 1884, but there's something called the Hart House here on campus, which I guess is some sort of like social whatever club, student hub. They didn't accept women on their grounds until 1972. And apparently JFK came and did a debate at Hart House in the 1960s. And women weren't allowed to go see this debate. And so there was a protest where women dressed as men and were able to actually make it into the lecture hall. They sat down, and unfortunately, some nosy security guards saw one of them wearing nail polish and kicked them all out. But yeah, so not too big a pat on the back, but at least, you know, the women could get educated, just not see the debates. It's fine. Okay, so Vera Rubin is someone who's going to check our work by Fritz Wiki. So we talked about gravity. We had our little Rubin astronaut. We remember that based off of how far away we are from the center of our mass, we're going to experience the force of gravity more strongly. It's going to be bigger. Or sorry, the further we are, it's going to be smaller. The closer we are, it's going to be bigger, right? Our astronaut feels a force of gravity more when they're standing on Earth versus floating out in space around Earth. So this is what we kind of think we're going to see when it comes to the motion of galaxies. And this is what Rubin saw. So Zwicky was right on track. Something seems a little fishy. I actually included her actual data. Yeah, so just as a side-by-side comparison, this is exactly opposite of what they were expecting to see. Now, how do we know as scientists what is wrong when we get exactly the opposite answer? So when scientists find something wrong with a theory, they have two options. Number one, your observation could be wrong. Maybe Rubin, despite all those nice little points and the nice diagram she drew, maybe she was wrong, maybe Zwicky was wrong. Let's go review it. And I'm going to fast forward here and let you know they weren't wrong. They were spot on. We kept getting these same results. Okay, so then option two, our model is wrong. So we have two models working here. We have our model for the theory of gravity. So maybe Newton got it wrong. It's been a while. What did he know? Or maybe our theory about galaxy structures is wrong. I'm also going to fast forward here and let you know that Newton's theory has been tested several times. There actually have been attempts to replicate Rubin's findings with modified Newtonian theories, and they can replicate it, but then they can't really match gravity anywhere else. So this is a probably not. Turns out Newton, smarter guy. Yeah, turns out when you make a theory that holds for like hundreds of years, you're kind of smart. So the other question is, what are we missing about galaxy structures? And the answer is missing mass. Okay, so yeah, there's something here that we're not seeing. Fritz was right. Like, we are seeing a greater effect of gravity out near the edges of our galaxy clusters. Yeah, so this is called dark matter. It is called dark matter because although it interacts with gravity like matter, it does not emit, absorb, or reflect light. So we all are made of matter. And actually, you are currently emitting an infrared glow. This guy does not emit anything, but is made of matter. When we shine our projector light on it, you can still see it. Dark matter does neither of these things. But it does interact with gravity, right? We're seeing the effects in our galaxy clusters. Okay, so a reminder, if you asked an astronomer 100 years ago what the universe looked like, and they looked at our little James Webb picture, they would say, oh, everything you see is what the universe is, and everything else is empty. And now, post-Rubin, we had this. It turns out that what we were seeing was such a small fraction of the larger piece of the puzzle. And actually, there's still one more piece missing. Anyone want to shout it out? Dark energy. Yeah, so this is now how we understand the universe makeup to be. Thank you all for interacting with me. It makes the process more fun. So this is where we're at. I always take an opportunity to plug this book because I think it's phenomenal. So Rubin was denied from Princeton. However, she had a husband who was also an academic who had been accepted into a graduate program at Cornell. And so she was able to go get a master's in astronomy at Cornell and later continue and get a PhD at Georgetown University. And if she hadn't done this, we don't know how far behind we'd be. I mean, you all saw that pie chart. It was 100% stars, galaxies, dust. Like, we would be so far behind. I would not be standing here because of an observatory that is trying to figure out more of this, right? Like, we are so lucky that she persevered. There are many who did not have the same story. This is a phenomenal book I recommend to literally everyone about one of the first 2 women to get a bachelor's of science degree in physics from Yale University. And you'll notice it says that she was the former director of the Master of Fine Arts program at the University of Michigan. So she actually didn't continue through physics. This is her book about why. So she went back and talked to those professors and tried to figure out where her trajectory changed and why she wasn't the next Vera Rubin. I mean, not in those terms. Vera Rubin was like kind of amazing, but you know. Okay, highly recommend. Let's talk about the observatory. Okay, this is the Rubin Observatory. I chose a particularly stunning photo. We have all the colors. Rubin is currently the largest digital camera in the world. It is going to take a complete scan of the entire southern sky every few days for the next 10 years. We expect it, because of this, to catch millions of supernovae. I'm going to throw some astro terms out here. Pay attention to the numbers. It doesn't really matter. Basically, millions of supernovae, more than 5 million asteroids, and 17 billion stars, 20 billion galaxies. Those are our estimates. So we're talking, I mean, this is a lot. This is going to catch a lot of stuff. By the end of its 10 years, it will have collected 30 petabytes of data. Has anyone here heard of a petabyte before? Oh, okay. Smart people. I didn't know what it was, so I looked it up in terms of gigabytes, which I do know because my iPhone is in gigabytes. It's 30 million gigabytes. That's a lot of data. I also wanted to compare to my iPhone again, just to see. 1 gigabyte on your phone can hold about 200 high resolution photos. So if you had a 30 million gigabyte iPhone, you'd have 6 billion photos. I have had my iPhone for 10 years, and I went to go check how many photos I have, and I'm at 12,000. So I'm just a little bit short, but yeah, the 10-year span, Rubin's gonna catch a lot more than I have. So let's talk about time domain astronomy, which is the next step of understanding why this is such a big deal. We're gonna go back to a little bit more of connecting this to Rubin here. Basically, much of astronomy was looking up at the night sky and seeing things, maybe taking a picture, and trying to understand what we're seeing. So in this case, we see a little figure. You know, he's got his little arm up. He's made of Legos. He's walking on Legos. There's some stuff behind him. But we're not catching everything that's going on here, because it turns out you could take photos along the progression of this little guy and put together a little movie that tells us a lot more. You'll notice in the background, things are shifting. He's moving and turning. So it turns out this is not his natural state. This is sort of the basis behind time domain astronomy. So we're trying to catch things that change over time, as opposed to assuming that everything that we're seeing that looks stagnant is going to be like that forever. Connecting this back to dark matter. So Rubin published her findings in the 1970s and gave us the most convincing evidence that dark matter is out there. And we have been observing it over and over again ever since. There is a method using time domain astronomy to see this, which involves something called lensing. What we're seeing here on the left-hand side is an image that has this sort of lensing effect. So basically, if you have a lot of matter between you and something in the foreground, in the background, and you have a lot of material, dark matter between the two of you, it can actually bend light because, again, our dark matter interacts with gravity, and it can sort of like distort the material as it's making its way towards us. So this actually, I also included a diagram here actually that's trying to show the same thing. Hold on, was this my little projector? Yeah, okay. So here we have a galaxy cluster, and on either end we have a version without lensing, and here we have, you know, our little foreground guy with our little dark matter as a little like black blob around it. And here's the difference between what we see when things are lensed versus not. And if you look closely, you'll see some of these galaxies have done complete rotations. We're getting some level of distortion here. So this is sort of like what time domain astronomy can show us, is that as things are moving around and they have some sort of like interfering mass between us and whatever this thing is, we can see these effects. Okay. So now I'm going to talk about where I come into this, which is something called a luminous red novae, and specifically, which Sophia mentioned, common envelope evolution. Okay, so I mentioned the word supernova. Who here has heard the word supernova before? Yeah, okay. So these are some of the most like energetic events in our universe. A supernova can have the same luminosity as an entire galaxy of like stars and gas and matter. So kind of hard to miss, pretty awesome stuff. This is not that. A luminous red nova to a supernova is what the light bulb on the right is to the light bulb on the left. So still something kind of bright, but not actually as bright as a supernova, which is why it's called a luminous red nova. And actually, if I wanted to be really accurate, it would be more like this. Because a supernova can be anywhere between 100 to 10,000 times brighter than a luminous red nova. And a luminous red nova can be 10 to 160,000 times brighter than just a regular sun-like star. So it's not that these things aren't bright, they're just not as bright. One type of luminous red nova is a common envelope event, which describes a binary star system in which binary stars, by the way, describe stars that are connected via gravity. Keeps coming up. We're thinking of our astronaut. Okay. And specifically, it describes a stage where one of these stars engulfs a companion. I like to think of it this way. Okay, so we have here a fossil of a fish. Anyone noticing anything a little weird about this fish? Yeah. Okay, I'm seeing, yeah, we're seeing something in there. Common envelope evolution is actually astoundingly similar to this. So basically, what we're seeing here is a fossil of a fish that ate another fish and died before it could digest the first fish. And similarly, when we take stagnant pictures of the sky, when it came to common envelopes, we were just seeing this like phase C or whatever. And we were trying to work our way backwards to understand our stop motion Lego guy. Yeah, so moving forward though, what we'd have is two stars connected together via gravity. For whatever reason, including just stars evolve and grow, our more massive star grows and engulfs its companion, and we end up with an orbit that's actually much closer than what we started with. I'm going to compare this now in a literature review, because why not? So we talked about supernovae, big popular field, rightfully so. You'll notice here we have over 4,000 articles that have been published on supernova. And the green bits here represent the number of those papers that are observational. So they're looking at real data and writing papers based off of what they're seeing. And you'll notice it takes up about half, a little less than half of our overall circle. Now we're going to compare this to common envelope evolution. Again, a reminder that we have been working in the field backwards from the sort of fossil fish image, meaning that actually a lot of our understanding has been overwhelmed by theory. So people with pen and paper trying to figure out how something could go from far away to that close. Or we also have numerical simulations. That's a huge chunk of our circle. Numerical simulations, meaning you are at your computer, you know, running a simulation to see what the final outcome looks like and comparing it to what you're actually seeing. And in terms of observational papers, we're pretty limited. And again, most of these have been surveys, which you'll notice say post-CE binary catalogs. Again, we're seeing our little fossilized fish and trying to understand what parameters we needed to get to that point. Okay. Common envelopes happen on the span of months, weeks, months, years, a decade. The decade thing is sounding very familiar now. What do we know that's going to be taking constant photos of the sky for the next decade? Anyone have a guess? Yeah, so I'm going to get the full movie and be able to figure out how we got from our bigger fish swallowing the little fish. Yeah, I couldn't actually find a little gif of a fish eating a fish, so I hope the penguin survives. But maybe it's a penguin. I don't know. We'll see. Yeah. Y'all, that was our history. Thank you so much for joining me on it. Okay. But big thanks to the AstroTours grad students for hosting this.
Thank you for the talk, Nikki. That's great. So we have the opportunity for a good amount of questions right now. So I welcome anybody to raise their hand and to ask a question of Nikki. Oh, right here. Perfect. Makes my job easy.
All right. Thanks. So you probably heard about the three theories that describes like the fate of the universe. So there is the remember correctly, there's Big Crunch, which is like gravitational is so great, everything's put together, and then there's the Big Freeze, where everything is like expanded to the point that it cools down, and then everything just like become dark cold abyss. And then there's the third one, I think it's called the Big Rip, where in Vera's Dr. Vera's observation, where the dark energy is like so great it rips everything apart, even atoms. So I'm just curious, like what exactly are the differences between the three, and based on Vera's observation, what you think would be the more likely scenario? Thank you.
Ooh. Thank you so much. Okay, did everyone hear the question? Okay, yeah. So the question, just to repeat, was about there are several theories about the final fate of the universe, which, side note, before you get worried, super far time away. Don't even worry about it. But we have plenty of time to figure out what's going to happen, is what I'm trying to say. Which is why scientists have quite a few theories, and we're not like super pressed to figure it out. We're kind of pressed, but you know, time-wise, it's fine. Common envelopes happening way faster. We want to figure this out. I want to figure this out first. But the question was, based off of observations for the different theories. So there's a few of like, you know, we know our universe is expanding to some level. We've had several observations that argue for basically a critical density of the universe being pretty much equal, meaning that we're on some sort of like a flat space-time. It's a whole thing. But the resulting like sort of end games of this is either you expand to a point and freeze, or slow down and just infinitely sort of slow down and stop. I say infinitely slow down, and then I said the word stop. There's no stopping. Infinite is infinite. There's a crunch where you get to a point where this stretches beyond its limits and sort of, actually, fun fact, this is how like massive stars go supernova. You can like hit limits where things like collapse back in, whatever. Or you can have some sort of like, what is it? We have a crunch, we have a freeze. There's a third one, the big rip. Yeah, okay. This is not my field, but I will answer from the Rubin point of view, which is that we'll probably have a much better understanding once we can understand better the basically dark matter and dark energy are sort of opposite forces to each other. So where dark matter interacts with gravity and pulls things in, dark energy is what's creating this expansion of our universe, or at least driving it. Rubin is going to give us a lot of information on both of these things. So we are going to have, in about 10 years' time, an unprecedented amount of information on both of those things to be able to better understand the balance, which will hopefully then give us a better understanding of how that's changing over the time. And then we can sort of model outward and go through the steps I told you about checking our theories and making sure things are good. Does that make sense? Okay. So I couldn't tell you now, but in 10 years' time, get back to me. Okay, more questions.
Hello, thanks for the excellent talk, Nikki. I was wondering if the Rubin telescope is a multiple mirror array, and to what extent it's affected by the 30,000 low Earth orbits satellites and other debris that's floating around there, and all the additional Starlink satellites that are going to pollute our view.
Did everyone catch that question? Ground-based astronomers' favorite question. What about all these Starlink satellites? The answer is it's ruining a lot of great data. They orbit pretty quickly. And basically what you'll get is, actually, if I go back to our gorgeous galaxy cluster, which again, that was James Webb Space Telescope. So it's outside of the orbit of these satellites. We don't have to really worry about it. But basically in our little nice, oh wow, this was so much further back than I remembered. Okay. This guy. In our nice little image here, what you get from these satellites is a nice streak right across. And so especially any like amateur photographer, like fanatics here. So like, yeah, okay. So if you want a nice picture, especially of a dark sky, one of the things you do is you increase the exposure time. This is also true for astronomy, which is why like the telescopes themselves. So the telescope is working with a 8 point something. I have the actual 8.3 meter primary mirror, and it is a series of mirrors. It then goes into, yeah, the largest CCD, like digital camera on the planet. I don't know what a Hexagon is, but if that sounds like I'm going to defer to you because you were the photographer. But yeah, so basically, as expensive as telescopes are to build, the mounts that are able, I mean, the sky is moving throughout the course of the night because the Earth is rotating. And so really like what the telescope sits on so that you can have an exposure time long enough to get something like this, you know, it can be like up to an hour, and that's like underselling it. So you need something that tracks with these things. And the velocity of these satellites is much faster. So what you get are these like nice little bars going directly across and ruining whole, you know, yeah. I mean, we have really fine data here that we could be using. And every satellite going up is just sweeping a nice little path right through it. So yeah, the answer is like, it's not great. And unfortunately, I blame Canada. No, I'm kidding. South Africa, no, it's the US's fault. Yeah. Did that answer your question? Yeah. Okay. Question? Oh, I saw a question.
Hi, thank you for the very fascinating talk. I'm interested in numerical methods for simulation, and I was wondering if like what makes common envelopes or the research of common envelopes more amenable to simulation than say supernovae, or is it just because it's a newer field, or like people are doing more theory, and what are the, and I don't know much about like astronomical simulations, so I'm wondering what are the differences from like if you were just doing regular fluid simulation, like what kind of things can really go wrong in such a large scale that you need to like do specific things with it? Like what do you find challenging? That's yeah.
Okay. Yeah. Wonderful question. I'm going to repeat it. So I'm going to separate it into two questions. The first one being, okay, so common envelopes, what makes, let's go back to our like literature review. Sorry in advance for the rapid clicking. Okay, we are at here. So what makes these guys more amenable to simulations than a supernova? And I'm going to direct your attention to the number right here in the middle for this guy versus this guy. So it's not actually that common envelopes are just more amenable to simulations. It's just that it was mostly all we had to go off of, right? There's been a far longer history of working on these guys. We have more observations too. So just trying to track what you're seeing with simulations has always made more sense. Versus for these guys, it is a lot of guesswork. So it's just overwhelmed by the fact that we're seeing way fewer of them. And we And actually the simulation methods are very similar, right? We're just working at different scales. The second part of the question was about astronomical simulations and sort of like how they differ from any other type of simulation. And the ideal answer would be not that much. Like fluid dynamics and a lot of like the theories that we apply here on Earth in like plasma physics or mechanical engineering and stuff, like, you know, nuclear physics, this is all going into these simulations. The question does become scale, but if you'll all remember from my bio, I'm a mathematician. So I'm actually in the little theory circle part of this guy, which means that I like to simplify things down as much as possible. And I approach things very analytically, where simulations will keep trying to add things in. I try to kind of go in and take things out and see if I can add a hierarchy to it. So, and if you were to ask me about what my simulation counterparts are getting wrong, it's that a lot of them do overestimate, or maybe the better way to say it is that they have a real faith in their simulations and the outcomes they're seeing. And many of them do forget to check against, I mean, we do know what these guys look like afterwards, right? We have our little fish fossils to compare to. And we've had a few cases where people get these crazy results and we say, well, but did you check to see if they're out there? And they'll say, well, the simulation said it, so it's probably out there. And it's hard to argue because, again, the number is pretty small. Yeah, so in terms of like how these things differ, yes, it's a scale thing, but in an ideal world, a lot of astronomy and the math we use in it can be applied in most of STEM, right? And I will also argue, luckily, that a lot of stellar astrophysics does not get to like the relativity, or, you know, there's some quant, but like for common envelopes, they're moving at speeds and stuff that's pretty okay to do some Newtonian and Keplerian assumptions, meaning that our good old friend Newton, all those hundreds of years ago, still right. Okay. Did that answer your question? Yeah? Okay.
Do you have any more questions? I'll come up here.
Thank you for the really, really interesting talk. I was wondering, in the case of common envelope events, I'm assuming that the reason you're using this kind of new data is because the mechanism is not that well understood. But to clarify, is it that two binary stars are orbiting and then one of them swells up to completely cover the other and then subsequently goes down in size? So there are both, once again, distinct stars orbiting, but the orbital distance has changed? Like, is this what you're seeing from these freeze frames that you have?
Okay, this is a great question. Let me make sure. Okay, I'm going to repeat it and let me know if I'm getting it right. Okay, so for these guys, so question about common envelope evolution, where just clarifying, we're swelling up and we're ending up with a much closer orbit. And is it because we're getting like reduced orbital speeds, or is it, okay?
Yeah, I'm definitely wondering about kind of the orbital speeds, if there is data for that you know, but also I'm wondering if that kind of B stage, is one of the stars completely covered by the other? Like, do they fully actually merge and then re-separate, or is that kind of what we don't know at the moment?
Okay, so then let me clarify. Okay, thank you so much for clarifying. Okay, so the question of when we have our like swollen, sort of more massive star, are we getting a full merger that then separates, or sort of what's happening here? Okay, so really great point, because the key to common envelope, it's in the name. So when you're looking at a star, especially as a theorist, we love to separate things out into the core and the envelope. The core being where our nuclear fusion is happening, and the envelope being the dust and plasma and like everything around it. So common envelope is literally a stage where you get this engulfment, your secondary, your companion gets eaten up, and you are completely shrouded from seeing it. So it is that they're sharing a common envelope, and that is blocking us from being able to see. So actually, a lot of my work in theory, is looking at those like snapshots and our stop motion. But what we're going to get to better understand these guys is really just how light is changing at the surface of these stars and how that differs from how that light would change if there was nothing inside of that star. So it's matching to anything that looks different in terms of like energy outputs, basically. Because as this guy orbits in there, it's dumping energy in, and that's reducing our orbit. And one critical step here that's missing, because this is a stagnant cartoon, is that you'll notice we don't have our envelope anymore. And so common envelope events, when I said luminous red novae, they're less energetic than a supernova, but still more than a regular star. They are going through a supernova-like explosion, just like much dimmer and much less energetic. So when you're losing your envelope between these two stages, you are getting this blast off. So yeah, does that answer? Yes, okay.
Great. We'll take maybe a couple more questions. Berg, I'll come over there.
I like it.
Gonna
Make
get
Sophia work for
Get
it.
my workout in.
Yeah.
Sorry, do you mind raising your hand again? I was looking at you, yes. There you go.
Hi, good talk. I was wondering about how AI is helping with the observational data now that I know like that they're using it to categorize things in the sky, and I'm wondering like because they're so close, these enveloping events, how it's able to kind of see in that kind of structure. Can you explain that? Sorry.
Oh my gosh, sorry. Did you have a follow-up?
No, that's it.
It was such a good question.
Do you understand?
Okay. Okay, so we have a lot of smart people working in the department who do machine learning and AI. I am not one of them. That said, 30 petabytes of data is like, physically, humanly impossible for us to go by eye, or even like with our codes churning along and like identifying these things. It would take, longer than our decade. And the goal is to be able to get this data in a state that it can be used as quickly as possible for astronomers to identify what's out there changing. So the answer is like, yeah, there's a ton of AI and machine learning being used by the Rubin collaboration. And actually, all the raw data that is getting collected by the Rubin Observatory gets immediately sent to what are called the Rubin brokers. So there are hubs at different universities or research centers where Rubin's raw data is being sent. And they were given this task as the telescope was being built. So they've had years to train machine learning algorithms and be able to identify different types of transient, time domain events. I do want to point out this guy. So has anyone, we're all getting very used to AI. We see that AI it's a stats problem, right? AI is going to show you the answers weighted towards what it's seeing most often. And so as a common envelope person, it is a bit concerning when a lot of what looks like my stuff is sort of gonna, it's gonna be overwhelmed. AI, like machine learning algorithms are gonna be so good at finding supernovae. Because look, almost half our pie chart over here is observational data that they can train on. And we have not that much. And again, it's all the aftermath. So it's going to be really hard for these machine learning algorithms to identify. So I'm probably going to get put in a bin called interesting thing maybe. And then I probably will have to find a way to sort through it. Yeah. That said, machine learning is improving every day, even at finding anomalous objects. And there are, again, smarter people than me who I'm working with to hopefully be able to. So my big, my dissertation was on creating predicted observables for Rubin of these events. So hypothetically, a machine learning algorithm could be trained on these things, and hopefully we can add a classification that doesn't just depend on the aftermath of these guys. We could have some sort of standard of what these kind of should look like. Yeah, but great question. Yeah.
Okay, let's thank Nikki one more time for a great talk.